Hi and welcome everybody to our presentation on UX for AR, brain surgery with augmented reality. As Theo just mentioned, my name is Catharina. I'll be walking you through the first half of the presentation, and then my colleague Lennart will take over. So as Theo just mentioned, we're both UX consultants at user interface design. So that means our main area of focus is user research and UX design. And today we want to present to you our research project Holomate. In this project, we got a lot of exciting insights, not only about the work of neurosurgeons, but also into the area of UX design for augmented reality within an emergency room. So next slide, please. Right, so Holomate is or was a project that was supported by the German Federal Ministry of Education and Research in order to better support neurosurgeons during a quite delicate procedure. We worked on the project with our partners, the Karlsruhe Institute of Technology and the Neurosurgical Clinic of the University of Ulm. And our goal was to support the so-called ventricular puncture, so that's the name of the procedure, by visualizing the ventricles in the brain via Microsoft HoloLens. So the ventricles are cavities within the brain that are filled with fluid, and you can also see them in the picture. Now, there are 4 ventricles in the brain, and the fluid inside brings nutrients to the brain and also takes away waste, for example. So this fluid is constantly being produced in the ventricles, and that also means that this fluid needs to be constantly discharged. Now, the discharge of fluid can be impaired when a person suffers injury to the head and develops internal bleedings, for example, in a car accident, or in other medical conditions like a tumor, for example. So when the fluids cannot be discharged, a pressure builds up inside the brain that needs to be released. And well, the way to do this is actually by drilling a hole in the skull and then releasing the fluid. So this is the so-called ventricular puncture. And in this case, when this happens, surgeons often have to act very quickly and also very precisely. Well, although it is a standard procedure, it's a routine procedure, the ventricular puncture often goes wrong. And so the first puncture into the brain is faulty in 1 of 3 procedures, and that's quite a lot. So the main reason for this is that the surgeon cannot see the ventricles and therefore doesn't know in which angle to insert the catheter. So ideally, the surgeon would have a hologram of the patient's very own individual ventricles projected onto the skull and also have a mark for the puncture site and the puncture angle. So this was our starting point for a research project. And as you can see, there is a need for such applications, but what is it really like to use AR in the ER? And would doctors appreciate such an application? So before even starting the research project, we interviewed doctors on their opinion about AR in the emergency room. And here are some of the results. So we asked, for example, do you think that augmented reality is an opportunity for the medical field? And as you can see, most of our participants answered that they do believe that AR is an opportunity. We also asked about the pros and cons of AR, and most of the answers were quite positive. So doctors mentioned that AR would well complement already existing imaging techniques, that it would support especially young doctors who have little experience with the ventricular puncture. They also mentioned that the visualization would facilitate their own cognitive representation of the ventricle, and that AR could be helpful for simulating operations and for operation planning. But they also raised some concerns that revolve mainly around the topics of additional expenses, so more time, money, and effort that goes into operations. So we also asked what the doctors thought would be the most important improvement that they hoped for with AR. So we asked which advantages would an AR system need to have. And in first place, they mentioned the patient safety. So that was the most important improvement that they hoped for with AR. Next, they mentioned work efficiency and support for doctors. And lowering cost was actually the least important advantage of using AR. So after this survey, we were pretty confident that the application would be quite useful and also accepted by surgeons. So next we did a couple of contextual inquiries. No, previous slide. I'm not clicking the slides, that's why we have to kind of find the right level. So next we did a couple of contextual inquiries in Günzburg and Ludwigsburg. And as you can imagine, it wasn't very easy to do this user research because usually it all has to happen very fast in such an emergency procedure. And we were lucky to observe a rather planned operation. So we were able to ask a couple of questions during the procedure, but also mainly observe during the procedure and then talk to the doctors afterwards. And they walked us through the process again and through the whole workflow. We were able to pick up some very important requirements from doctors in these contextual inquiries. For example, they were very concerned about making sure that the ventricle hologram really matched the patient that was laying on the operating table. And they wanted to be able to double check the patient's name and the CT scans. Or when we first introduced the AR procedure to one doctor, he raised concerns like, well, but the hologram can't just be a standard ventricle because that wouldn't help him in his work. It had to be the exact hologram rendering from the patient CT scan. And then he asked, well, how can you automatically create a hologram from CT scans? Because, and here the term automatically is very important because nobody has time to create a hologram when there is an emergency, right? So requirements was one very important part of the user research, and another part was the environment. So a couple of things that we picked up about the surrounding was that the lightning intensity was quite normal. Next slide on lightning. So the lightning intensity was normal, but there was very strong light directly above the operation area. And we had to keep that in mind when designing the hologram, because of course the visibility of the hologram would suffer when there is too much light there. Temperature was normal, and it was rather quiet in the ER. There were just sounds from vital signs and patients. So, and this is also important to keep in mind when you think about interaction methods such as voice commands, for example. And we observed some movement around the operation table from time to time. Right. So in our contextual inquiry, we looked at the whole workflow. So that's preparation, implementation or operation, and then the follow-up and documentation. And after the user research, go back one slide, please. And after the user research, we began conceptualizing and designing a solution. So conceptualizing a solution also meant asking questions like, when we look at preparation, for example, who cleans the HoloLens before and after the operation? Is the HoloLens even allowed in the ER because of cleanliness policy, right? Or when we look at documentation, doctors told us that they often get called into the next surgery right away and don't have time to document the surgery. Sometimes they get around to documenting it the next day or maybe days afterwards. So we also looked at questions like, how can the HoloLens help doctors to document the procedure? So overall, there were quite a couple of things to keep in mind when designing the application. And my colleague Lennart will shortly walk you through the design process. But before that, we brought you a quick video, a quick sneak peek at what a test operation looked like. So that was a very quick video of what the test operation looked like. And now it's your turn.
Thank you very much. Then I'll take over from here. So this is what the currently implemented and working version of the Holomate application looks like. And we've developed an augmented reality app that's called Holomate that allows neurosurgeons to project the 3D model of the actual ventricular system directly into their field of view. And therefore, we work together with the Institute of Technology in Karlsruhe, and they developed an algorithm that can calculate an exact 3D model of the patient's ventricular system based on CT scans, and that even works within seconds. Here's another angle of the application. You can clearly see that we've worked with large, bright buttons, which can be seen in every bright surgery light. And the application is controlled almost exclusively by the user's gaze, so the direction he turns his head. So he doesn't have to take his tools apart or move them away. The whole app is aligned with the workflow of the operation. Yeah, just let me walk you through it. So this is the app in its default state. The app has been developed in Germany, and therefore we see a German language version here, but I will translate all important terms for you. So the neurosurgeon starts with Vorbereitung, which means preparation in English. Here the surgeon has the opportunity to get an overview of the situation with a clear view of the patient. And he also has the possibility to display important information such as CT images and a 3D model of the ventricular system. And on the patient's head in the middle of the screen, you can see a small blue ring that indicates where the user is looking at the moment. And this shows where its head is facing right now. And he can some sort of control it like a mouse on a PC. And as mentioned, the app is operated via gaze tracking. So the user must therefore look at the corresponding button and stay there briefly to activate the button. And this process is visualized by an animation along the contours of the button. You can see it here, and this takes around a second until the button gets activated. You will see a record of the app later where you can see how this looks like. So this is what it looks like when the ventricular system is displayed in the field of view. It's an actual 3D model, so you can move around and see it in space. And there's also the possibility to show CT images of the patient right next to the patient's head. And the user can even scroll through them to find the image he needs. In the next step, that's called Kocher point or Kocher Punkt. Changing steps works the same like the buttons on the left with the long gaze method. In the next step, you can see the so-called Kocher point. That's the point where at which drilling is done and the catheter is inserted. You can also see the construction lines along anatomical landmarks so that the surgeon can check the accuracy and make sure that everything is on its correct place. And using the L and R buttons, you can decide whether to operate on the left or on the right side, because this decision sometimes happens very spontaneously. In the next step, Schnitt, which means cut in English, you will see a marker for the cut. More importantly, the surgeon can document the time of the incision with a voice command. And in the last step, Winkel, which means angle, the drilling and insertion angle for the catheter is displayed. And the surgeon only has to align his tool along the angle in order to optimally hit the ventricular system. And additional lines and a square are shown at the end of the angle and these help tremendously to understand the three-dimensionality of the hologram. And to prevent the doctor's tools from being covered by the hologram, the opacity of the holograms pulses, so we can always see his tools behind the holograms. Here you can see a recording of the app. It's a record directly from the Microsoft HoloLens, so you can see it actually works. And I hope you can see the video without big glitches or something. And you can also see here that the HoloLens needs a QR code placed in the field of view as a tracker. And this ensures that the three-dimensional tracking always works correctly. And here you can see the pulsing of the holograms to make sure that the tools are always visible. And of course, later on, we tested and tweaked the final product again in the operating room with real neurosurgeons. And we find out very interesting things there. For example, we tried out several color variations. We started with the assumption that red light was the least glare to the eye. But we only realized in the operating room that red holograms are hardly visible on the patient under the strong surgery lights. And blue light stood out best in real environment. And so we tried out every color possible, and it just was the best way to go. And it also has the additional effect of keeping you awake. And this is only a small example of how important it is to work iteratively and to carry out tests again and again. Yeah. So we come to the end here. We hope you have gained an exciting insight into our approach to this project. Thank you very much for participation. And if you have any further questions for us, please feel free to contact us.
Thank you very much, Catharina, and thank you very much, Lennart.
Okay.
Yeah, some interesting things that people wanted to know. Was that a dummy that they were working on? Please say yes.
Yeah, of course. Yeah, it would take a lot of more tests to be able to do this on a real person. But
okay.
But in the research phase, we also watched real operations, so it's not just all imagination.
Okay, great. And that's in surgery at the moment, I'm assuming. That's actually within surgeries at the moment, or within hospitals at the moment. They're using your augmented reality.
No, not
no,
yet.
actually. No, because the tracking is not good enough yet to really use it in surgery. It has a lot to do with well, the tracking has to be a bit better to really use it on patients. So it's a prototype right now.
Okay, I'm with you. Thank you. So we're going to take a couple of questions quickly. So we have a question here from Benjamin, and he's asking, was the limited field of view on the AR device HoloLens an issue?
No, actually, it also helped because it reduced the holograms that the surgeon sees while he's doing the surgery. So he got a better focus on his work by that. It's not just a problem; it's actually a benefit.
And we also asked that in user research, and had the surgeons put on the Microsoft HoloLens, and they said, well, it has a very limited field of view. We were working with the HoloLens 1, not 2. But he said, well, actually, when you're operating on somebody, you just need to focus on one space, on one point, really. So it doesn't really, so it's not a disadvantage, yeah.
Okay, super. Thank you for that. So we have another question here from Tim. Is how have you managed different product releases, upgrades to HoloLens? Did you have to stick to one version until testing new release?
I'm not actually sure about the programming, but I didn't notice any problems from our coders or software engineers. They haven't mentioned any problems from that side.
Yeah, well, I just know they implemented it in Unity, and that they did it for the HoloLens 1, and yeah, So they didn't mention any problems really. Yeah.
But I know that they always stuck to the same Unity version, the whole process.
Okay. Thank you. So we have a question from Sabina. Is there already any empirical data on whether the 1-to-3 ratio of failure has improved, even if it's just the prototype?
With our prototype, we actually had a 100% success rate, but we just tested it on dummies, like you saw. So that's not a really reliable,
accurate
rate in that way.
Okay.
So we got over 50 tries in this prototype, and they all hit perfectly.
Okay. So Tobias has got a question here, and his question is, wouldn't it be easier to let this do by robot?
Well, our next research project might be about robot assistants in the ER. I'm not quite sure where the research in this area is at the moment, but looking at where operations are at the moment, well, most of the operations are still done by humans. So, but this might be a good start for a new research project, actually. Yeah.
Yeah. Okay.
Right.
Fabulous. Thank you, Lennart. Thank you, Catharina.
You're welcome. Thank you very much for having us.
Thank you. Thank you for sharing. So we'll just end it here.
Thank you. Bye.
Thanks.